All right, welcome back to Mr. P Helps with Calculus. This is Unit 2, Day 1, as we explore the difference between average rate of change and instantaneous rate of change. All right, so we start with a quick warm-up, which I know I usually skip warm-ups, but I'm going to go over this one. Difference between a secant line and a tangent line. Should have learned back in geometry. Secant line is a line that goes through a circle and intersects it twice, whereas a tangent line is a line that only intersects a circle once. So this would be a tangent line. This would be a secant line because it only hits this function once. All right, so now that we've explored the difference between those two, so that's kind of the difference of what we're doing today. So secant lines are going to be lines that show average rate of change. So if I give you this blue function and I ask you to find the average rate of change from this point, from A to B, basically, so this is the height of A, f of A, and this is the height of B, f of B, and you wanted to find the rate of change, or average rate of change, essentially what you would do is just use the slope formula, which you've seen this before, that y sub 2 minus y sub 1 over x sub 2 minus x sub 1. All right, so that's how you would find the average rate of change. So that shows you how much it increased over time on average. Now, obviously, the slope of this curve was not the same the entire time. It was going up a little bit faster, then it starts going up a little bit less fast. But on average, this straight line shows you the average rate of change. Now, we could find average rate of change by just taking the 2 points, like I said, and plugging it into that formula, that y sub 2 minus y sub 1. You can see the two examples, but this is something that you should be familiar with. So from this point to this point, sometimes it went up, sometimes it went down, but on average it went up one right, one 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 up one right, one. Or, yeah, so I guess I started or ended in the wrong place, but it looks like it's going to be going up one right, one on average. Now, talking about instantaneous rate of change, that's going to be something totally different because that would be your rate of change at that instant. And we'll get to that in just a second. It says, okay, this is still average rate of change, so we would just plug in -2 into this function, plug in 2 into this function, find the height at those 2 points. That's essentially what you're doing. You're finding f of -2, and you're finding the height at f of 2, and then you're using your slope formula to find those answers. All right, but really we want to get into and explore what is instantaneous rate of change. Now, we don't have a secant line anymore. This is a tangent line. This line is only hitting this function once. Now, you can't really find slope of a singular point. You would need 2 points. You would need to do that y sub 2 minus y sub 1. So instantaneous range is just a way of finding the derivative. So derivative just means, that's how fast that the tangent line is increasing at that particular moment. Now, we use notation for that. We call it f prime of x. That's the derivative of x. Now, we use different symbols like d dx. We could say d dx of a function. The x function could be just x squared. It could be any function, and we'll learn how to find the derivative of all kinds of different functions over this unit. So that would just say the derivative of this function. dy dx means the derivative is. So dy dx is, it could be 2x. That means that this function is the derivative of the original function. Or df dx means the derivative of f with respect to x. So that is another thing. So how this is read, when it says dy dx, that means the derivative of function y, of y. So you could have an equation like y equals x squared. So that would be y. So that's dy dx. That's the derivative of y with respect to x. Or d dx, find the derivative with respect to x. All right. It's pretty common to say with respect to x because that's really how we normally write equations. It could be something else, but it's very rare that it's not going to be with respect to x. But you'll see that in the future. Calculate the instantaneous rate of change. So we have 1 over x, which is in blue. If we want to find the instantaneous rate of change at 1, which is right here, that would be this green tangent line. Now, this green tangent line is going down one right, one down one right, one down one right, one. And we've chosen that on purpose just because it would be something quite easy in this case. And we're going to explore that. So basically how we're finding, okay, I went too far. Okay, so this is the rate of change of this function. Now, if we have a different function, different green function here, now this is a little bit harder because I can't actually manipulate this. I can go to this website, GeoGebra. And what essentially you're going to do is you're going to mouse over B, and you're going to move it closer and closer until it gets closer to A. Now, what you're trying to do is trying to change the rate of change. Now, if you connect A to a closer point B, what you're going to notice is that this dotted line, that secant line, that blue line, is going to get closer and closer. If you leave A where it is, and you just slide B down this curve of the function, it's going to make this secant line closer and closer to the pink tangent line. As soon as you get B so close to A that you can't even see anything in between it, the tangent line and secant line is going to be almost exactly the same. That's essentially what we're doing for instantaneous rate of change. We're squeezing it down, those 2 points, so that they're getting as close as we can possibly get it in between them. So we are approaching the fact that B and A are on the exact same point. Now that's important. We are approaching that. We are approaching a distance in between A and B of being 0. And that's how we're going to use limits in order to find derivatives. That's the first way we find derivatives. Later on, we'll find other ways of memorizing them. Now, using our limits in our calculator, this is the old way of doing this. This is the same question I was mentioning a second ago. We take a point that's on the left of 1. We take a point that's on the right of 1. Something a little bit less, something a little bit more. We plug it into our formula, which is basically our slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, right? That's your difference between A and B. So in other words, you're taking a B that happens to be on the left side just barely, on the right side just barely. And what you notice that when you use your calculator to solve these, you get essentially the same answer. You get something that's a little bit less than 1 and something that's a little bit more than 1, negative 1, sorry. And essentially, you're going to notice that these two are approaching a slope of negative 1. So negative 1 is in between these two answers. Like I said, it's just approaching because you can't actually make it A and B the exact same point unless they are exactly the same point, which is literally what we're trying to do for a derivative. So you're squeezing it down and you're making the limit approach 1. So you're trying to make the limit approach 1 because 1 is what we're trying to find in this case. So as f prime of 1 is, now we're using that function of 1 over x. And what we're doing is we're using, this is one of the 3 ways of finding instantaneous rate of change. This is our limits for, or these are our limit definition of a derivative. There's 3 formats for this, and this is our first one. This is our f of x, our original function, minus if you put whatever the x value is, whatever the x value is approaching, it's in this case, it's going to be 1. So if you put 1 into the original equation, you put that here, and then you just put over x minus whatever that number is right here. And then you can solve for it, and you can see that I solved for it all the way down until I got to negative 1. By crossing out the holes, you're able to, the x minus 1's here, you're able to get rid of these 2 right here, so therefore you're able to actually find the limit by plugging 1 in for x and solving. And you can see we get the exact same answer. So yes, this does work for finding the derivative at any given value. Now, to practice this, here's another question. So this is our f of x. This is our a. That's what x is approaching. It's approaching negative 3. So this is f of x right here. And this is our f of a, meaning you're just taking this a term and you're plugging it into what x is. You're plugging negative 3 in for x. Negative 3 squared is 9. And then you're putting it over x minus a. So x minus negative 3 is on bottom. Solve that, and then you can get rid of that hole by factoring the numerator. And then you plug in negative 3 in for x. Negative 3 minus 3 makes negative 6. And there you go. And that's our first time of using limit notation in order to find the derivative at that value. So in other words, what you could do is verify this with a graphing calculator. If you put x squared into a graphing calculator, and then you put the trace at negative 3, you should see the slope should be at that point about negative 6. The slope of the graph should be going down very quickly because it's a parabola. Now, I'll do my best to kind of graph what I'm talking about here, but obviously it's not going to be perfect. So this is the parabola. So at negative 3, that slope should be about -6. And this would work for any x value. You could use this exact same equation no matter what x value it is, because this is going to be differentiable on the entire time of the function, which we'll get more into in a future video. Thanks again for watching, and I'll see you again in the next video.